Computationon Encrypted data. And I would like to invite Mr. Rohit Khera. Mr. Rohit Khera is a distinguished engineer at Marvell Technologies with a strong background in applied cryptography protocols, numerical physics, and software. He also worked extensively on lattice cryptography, fully homomorphic encryption, multi-party computation, and systemic zero-knowledge arguments. His work focuses on optimizing sub-operations in FHE schemes, such as rescaling or linearization of tensor ciphertext, boosted key switching, automorphisms on packed ciphertext, and the representation on non-linear functions in encrypted domains for ML inference. So,
Thanks for attending this.
Thanks for attending the session. We are going to talk about homomorphic encryption, and this is a little bit about me. The gentleman has already given me an introduction, so I'm just going to skip over this slide. This is an alternative title for my presentation because most people understand or might have heard about homomorphic encryption, and if you've heard about that, you might think that it's a simple question of encrypting and decrypting data. But it's actually significantly more expansive than that, primarily because of the fact that we want to compute on encrypted data. So in order to do that, our crypto system has to incorporate a set of universal gates in order for us to be able to compute arbitrary functions on encrypted data. And that brings in a lot more machinery and mathematics than would otherwise be required for a simple encryption scheme. So as we step through this presentation, I hope that becomes more apparent. So here's that's just an alternative title for the presentation to dispel some confusion about what FHE or homomorphic encryption actually is. So just some basic motivation here. This is some information from Verizon going back to 2023. The actual number of data breaches was higher in 2023. These are just the breaches that resulted in data compromise or exfiltration. And of course, the types of information that were compromised just, range, fall within a wide spectrum of different types of data, intellectual property, customer data, etc. So what is the nirvana here? Well, the nirvana here is to be able to compute on encrypted data. If we had a cloud provider that was custodying our data and doing some computation on it, well, wouldn't it be great if that data was just always encrypted? And the cloud provider, and for that matter, an adversary that a compromising cloud provider simply wouldn't be able to access the clear text at all. So this is the notion of computing on encrypted data, computer program working purely on encrypted outputs. And of course, this could happen on the cloud, which would make it secure in the case of an organization having to place its data outside of its actual data network perimeter. Okay, so you might think this is just a dream, but it's more than a dream, it's a reality that's coming true. This is some information from IEEE, and then there has been a fair amount of patent activity in this area as well. So here's a basic agenda. We're first going to talk about computation on unencrypted data, and then we'll progress to how you do this on encrypted data. And rather than giving you a sort of formal treatment of the subject, we're just going to dive into an actual example to give you a flavor for what these systems look like. And the example that we're going to use is a very intuitive example, which is search on encrypted data. So that's the basic blueprint for this presentation. So let's talk about universal computation on unencrypted data. So all of these mechanisms are Turing equivalent, and they're all Turing complete. So with any one of these systems, we can actually express arbitrary functions on data. The paradigm that we're going to focus on is circuits. Now we all know about arithmetic circuit, or rather Boolean circuits, which are networks, directed networks of Boolean gates. Well, Boolean circuits are actually a subset of a more general class of circuit, which is called an arithmetic circuit or an algebraic circuit. And rather than having binary gates, you have what are called arithmetic gates. And in our case, there are effectively three types of arithmetic gates. There's addition, multiplication, and there's this special gate called an automorphism that helps us permute data, encrypted data that's packed into an array. So it helps us do rotations, cyclical rotations and permutations in encrypted data that is vectorized in some form. Okay, so Boolean gates have simple operands, 0 and 1. Arithmetic gates have more complicated operands. They can be integers modulo q, or they could be polynomials with coefficients drawn from integers modulo q. So before we jump into this, in order for me to give you some intuition about how these systems work, we are going to have to get into some mathematics. But I assure you this is all just high school level math. We're talking about polynomial multiplication and addition. In fact, we won't even get into polynomial multiplication. We're just going to stick to addition. And then we're going to do modular arithmetic. So just a quick recap on modular arithmetic. 6 times 3 modulo 5 is 3. Okay, that's good. So let's take that number 3. 3 over the integers, right? So let's do 3 plus minus 3 over the integers. That gives us 0. Now, if we do 3 plus minus 3 mod 5, that really doesn't make sense, because minus 3 is not defined in the integers mod 5. But we can do 3 plus 2 mod 5. That gives us 0 as well. So actually, mod 5, 2 is the additive inverse of 3. Does that sort of roughly make sense? Okay, good. This is all we need to know in order to progress. So here is a simple example. Now I've chosen coefficients modulo 97. That was maybe a little too ambitious of me. I should have chosen a smaller modulus, but let's just stick with this. So we're going to add 2 polynomials where the coefficients are drawn from the integers modulo 7, rather modulo 97. And so, of course, as you can see here, we just gather the terms, this 65 plus this, well, let's look, 70 plus 49, let's look at this x squared term. That gives us 19 modulo 97, we get this 22. So that's pretty straightforward. We just add polynomials and then we reduce the coefficients for each power of x modulo 97 to get the result. Okay, so now let's do a search for an element in an array. Assume your pattern that you're searching for is this polynomial over here. So you're just searching for the sequence 19, 32, 27, 16. And you've got a target array that contains 2 elements, 0, 49, 49, 0, and here you see this polynomial over here, 19, 32, 27, 16. Okay, so how are we going to see if this pattern exists in the target? We're going to use our circuit-based definition, or express the search function rather as an arithmetic circuit using the plus gate. So what we do here is the first thing we do is we get the pattern and we negate it. And as before, when we wanted to negate 3 mod 5, we got 2. When you negate the coefficients in this polynomial over here, you wind up with this polynomial as its additive inverse modulo 97. So then now let's go ahead and simply add this negation of the pattern to each element in our target array. You add it to this polynomial, you're going to get this result. Whereas if you add it to this polynomial, you get this result. So immediately what you can see here is 0 is a sentinel or a distinguisher that tells you that you've got a match. Because this, when I add the polynomial to its additive inverse, I identically get 0, which signals a match. Okay, so that's pretty simple. Now, but that's not really computing on encrypted data, right? That's just, I'm just letting those polynomials sit out there in the clear. So how do I make this private? Well, I'm going to make this private. Well, in order to do that, we've got to get into universal computation on encrypted data. Now, unlike computation on structured data or unencrypted data, where we have different paradigms, we can really only compute on encrypted data, compute functions on encrypted data, if those functions are expressed as arithmetic circuits. And once again, those circuits comprise polynomial multiplication, polynomial addition, and this special operation called automorphisms. So let's go ahead and figure out how we can make this search private. Well, the first thing we do is we encrypt the messages that we would... Yeah, go ahead.
Did you say that this algebraic circuits, they are also truly complete?
Yes. So, as it turns out, so if you look at Boolean circuits, I think it follows from probably De Morgan's laws in first order logic. An AND gate and a NOT gate are Turing complete over GF2, over 0 and 1. And similarly, polynomial addition and negation are Turing complete in the underlying polynomial ring. Okay. So how are we going to encrypt the message? We have, so let's take a normal let's take a clear text polynomial, and what we're going to do is add noise to this polynomial. And so what happens is your message is now living in the noise, and so it's being masked by the noise. And in order to decrypt, what we do is we take that ciphertext, which contains the noise term, and we subtract the noise to get back the original message. So what does this actually look like? The noise is also a polynomial, and it contains three distinct elements. This first element is a product of a special polynomial AX, which is a public parameter. This second polynomial is the secret key polynomial. It's a secret polynomial that the encryptor possesses. And then we add, or rather that the data owner possesses this polynomial. And then we add an error polynomial. And so this term is called the secret mask, and then this term over here is called the error. And so there is a condition that we have to meet here, which is that the norm of this error polynomial has to be much smaller than the norm of this polynomial. But other than that constraint, there are no other constraints. We sample these polynomials from the underlying set of polynomials that we've chosen to compute upon. So encryption is pretty simple. We take our public mask here, we add the error term, and then we have a message, which is also a polynomial, as you saw before. And so what we simply do is we add these three terms to the message to get a ciphertext. Seems pretty simple. And then, in order to decrypt, as the data owner, I possess, so for example, this is actually a public key. I can just publish that. And in order to encrypt, if someone wants to encrypt a message, they take my public key and add their message polynomial, and then you get a ciphertext. Now, if I want to encrypt that, I happen to know what the secret key is because I'm the data owner. That's my secret key. And this polynomial a of x is a public polynomial. So I simply construct the secret mask, I subtract it from the ciphertext, and I get the message plus the error term. And because the L2 norm, or the coefficients of that error polynomial are small relative to this polynomial, I can use error correcting codes in order to recover the original message. I'm not going to get into the exact science of the error correcting codes here. There's a few different choices. The most popular ones that are used are from quantum error correction. But just know that there's ways for me to take that error out once I have unmasked the message. So now we can go over our previous example and do this in encrypted fashion. So I have my two polynomials. I take the first polynomial and I add a noise term. I take the second polynomial, I add my noise term. And then, as before, I can add these two polynomials, and I get a result with the additive noise. Okay, so that's pretty straightforward. So now what I can do is, if I have this sum of two ciphertexts, it's going to look something like this, right? So if I have, say, my original polynomial was just x, and then I encrypted it, or say that I get x as the product of adding my two polynomials, but I'm going to get those two additional noise terms. And then to decrypt them, I can simply subtract the two noise terms to get back my result, resulting from, say, the addition of these two polynomials, and I simply round it off back to x using error correction. Okay. So now we can use this blueprint in order to actually do encrypted search. So what we're going to do here is we're going to take our a pattern here and a pattern here. So this is our target array, and we want to look for we want to look for, in this case, this polynomial. We want to look for this pattern in this array, in this encrypted array. So the first thing I do is I get this pattern, and the first thing I'm going to do is I'm going to calculate its additive inverse. Its additive inverse is simply this polynomial over here. I add these two polynomials, I get a 0 plus the noise 1, noise 2 term. Whereas if I add these two polynomials, here's the inversion of the pattern that I'm looking for, and this is the target element in the array. If I add these two, I do not get 0. So what can I do with this? Recall that 0 over here is a sentinel or a distinguisher that tells me that I have a match of this particular element in the array. So I simply give the results of this search to the end user, and the end user can decrypt it. And when the end user decrypts it, they go ahead and they see that they have a way to unmask the noise, and they see that for this element I get a 0 sentinel, which signifies a match in the second element, whereas for this one I do not get a 0 sentinel, so therefore I do not have a match in that element. So that's really it. That's the crux of the matter. Now, when we actually talk about doing this in real life, we typically use polynomials of degree 64k. So these are very large polynomials. Univariate polynomials in x with about 64k coefficients, drawn from integers modulo a prime number that is typically in the order of 1,000 bits. So each coefficient in the polynomial is around 1,000 bits. So of course the scale of the problem increases greatly when you start, for example, multiplying two degree 64K polynomials. I just wanted to touch upon the security of this. So you can go back and look at the construction of the actual ciphertext, which is this. It's this secret mask over here with the error plus the message, which gives you the ciphertext. Now, the security guarantee that you get from this is we assume there's some polynomial, there's some PPT adversary, polynomial time adversary with random coins. We assume there's some problem, hard problem in NP, SVP gamma. Actually, this is not just an NP, it could be in quantum Merlin Arthur as well, because the scheme is quantum secure. And then, of course, we assume that there's no intersection in these two sets. So then the theorem says, if the adversary is such that I give the adversary this polynomial, and the adversary can, in polynomial time, give me S, then I can use this adversary as a subroutine in an algorithm to solve SVP gamma. But number theorists have been looking at SVP gamma for a very long time, as in over 150 years. And they have not found any algorithm to break SVP gamma, or to say that SVP gamma is in P. It is firmly in NP. However, if this adversary exists, it implies that SVP gamma is in P, so this adversary does not exist. That's your fundamental security guarantee right there. Okay, so that looks pretty simple, but as I said, when you start doing this in real life, you're using polynomials of very high degree, 64K, which is typically ideal. And coefficients of each one of these terms in the polynomials is up to 10K, rather 1K. So that results in a lot of different machinations that we have to do in order to keep the ciphertext clean. So a lot of ciphertext maintenance and hygiene operations that come into play, which we're not really going to be able to get into. Well, maybe we'll be able to get into some of it. But yeah, in practice, this becomes really quite complex. And that's primarily because of the expansion in the data size. Just to give you an understanding of the overall system operations, we have encryption and key generation, so this is usually going to be done on the client. Client will generate key according to the parameters and the security strength that's desired, and then encrypt the data that will be passed on to a third party that will now compute on the data. And these are basically some of the primitives that will be used to compute on the data. As I said, multiplication and addition. Those are your basic gates in your arithmetic circuit, and then the permutation gate that I talked about earlier on using the automorphisms. This is one of the cornerstone algorithms. We don't multiply two polynomials in the coefficient domain because, for example, multiplying two 64K polynomials, well, that's prohibitive. So basically, what we can do here is we can go from the coefficient domain into its Fourier conjugate, which is the evaluation representation of the polynomial, where at that point, multiplication is just component coefficient-wise in the conjugate domain. So this number theoretic transform is effectively an FFT on the polynomial, but over a finite field, over integers modulo q, rather than over the real numbers or the complex number field. Bootstrapping is a way to refresh the ciphertext. What happens is with successive multiplications of the ciphertext, the error term in the ciphertext starts growing, and at some point the multiplicative errors will violate the condition that the norm of the error has to be much shorter or lower than the norm of that other polynomial. And we're talking about a simple norm. It could be an L1 norm, or it could be an L2 norm. Pick your norm. So bootstrapping is a way to get rid of the error completely and change the ciphertext that is encrypted under key A, for example, into a ciphertext that is encrypted under some different key B. And that process eliminates the error completely and gives you, basically resets your error budget to do more multiplicative computations on the ciphertext. Key switching is another primitive here that is related to bootstrapping. Rescaling is a way to basically constrain the growth of the coefficients of the ciphertext. So for example, if I have 32-bit coefficients for each one of these polynomials, I'm gonna multiply those two, I'm gonna get a 64-bit result. I need to rescale that back into a 32-bit number. But I need to do that in a specific way, and so rescaling is a primitive that allows me to do that. And then the CRB is a specific operation. I'm not going to get into that here. But if you look at the relative timing, then you start to understand some of the overhead that's involved. Key switching being probably one of the heaviest pieces in this whole scheme, along with these automorphisms or these permutations that allow you to do rotations on ciphertext arrays. This was a benchmark that we did with polynomials of degree 64K. And the actual coefficients of each one of the coefficients of these polynomials was around the order of 700 bits. The key generation is also pretty heavy, but these are just one-time operations that are done on the client, so we don't really care about that. Okay. So just to give you a little more information about the benchmarks, this is a famous benchmark that is used not just in homomorphic encryption, but in other forms of computing on encrypted data like multi-party computation. So the idea here is that you take a piece of data and you encrypt it under the homomorphic encryption scheme. And then what you do is you take an AES key and you encrypt that according to the homomorphic encryption scheme as well by the same public key. And then what you can do is you can apply the AES function homomorphically on this data block so that you can double encrypt this data block. It is AES encrypted wrapped around in a layer of homomorphic encryption. So this takes about 2.5 seconds per 60 bytes. This is on an Intel Core i5, whereas you do this, on an accelerator like our CPT block, you're looking at something like 0.06 microseconds. So there's several orders of magnitude in terms of the additional time that's required. Okay, let me take a pause here. Any questions thus far?
I'm just a little confused with the second part, when you say that it's 0.06 microseconds in the plain text domain.
So I'm sorry, this is not on the CPT block. If I was just doing it, so what I stated there was incorrect. This is all in software, by the way.
Right.
If I were to homomorphically evaluate the AES function, that would take me 2.5 seconds per block. But if I just took this data block and AES encrypted it in the clear text domain, it would take me that long. I think this is with OpenSSL, if I recall correctly. Does that make sense? Information about this. But it's not a simple question of just, implementing the AES function homomorphically and then accelerating it. The big problem here is data movement, because your polynomials are very large. You can't cache all of them in SRAM. So, that's really the data movement, once again, is the main bottleneck. But yeah, there's no real definitive benchmarks around what this would look like on an accelerator.
Thank you.
for MNIST handwritten digits. I think the usual CNN is 9 layers, but this one's just abbreviated to 5 layers. So you can see these are the convolution, they're applying the kernel at this stride, 46 seconds. So that's pretty heavy. For an MNIST image, I think those images are, I think those are 10 by 10 pixels, if I'm not mistaken. So we're not talking about very large. One approach is to take the mathematical operations related to things like key switching or bootstrapping or multiplication, and to create specialized functional units to encapsulate those pieces of functionality. The other approach is to take a general grid computing approach, where you just have something like a systolic array or a large array of multiply accumulate units, and then you have some way to reconfigure the hardware for your specific functional unit. So those are, broadly speaking, the two directions that are being taken in the industry. Most of the companies that that are expected to tape out this year are using the FU approach rather than the generic reconfigurable fabric approach. But one of the firms is taking that approach. So it's going to be interesting to see how those compare as we get data on those systems. So this is one possible decomposition of the operations into different functional units. There are other ways to decompose this problem as well into different types of functional units. And then this is just generic infrastructure that you need to have. So what are the key challenges? As I alluded, data movement is a key challenge. We get at least a 50x expansion in the data, and we find that 25 megabytes, so that corresponds to 64K polynomials. That's about optimal for some of the schemes that we're looking at. And then the computation requires auxiliary data, specifically for things like bootstrapping and key switching. And in the original schemes, the 25 megabyte ciphertext was accompanied by around 1 gigabyte of auxiliary data. And now with some advancements in what are now, I guess, the 4th or the 5th generation FHE schemes, we can get that auxiliary data size down from about 1 gigabyte corresponding to a 25 megabyte ciphertext down to about 100 megabytes. So we need to somehow move about 125 megabytes of data in and out of this compute fabric. And that's really the key challenge. So any kind of a hardware fabric is going to have some particular pipelining or layout of the functional units. And then the whole problem becomes we have this arbitrary application that's expressed, arbitrary function that's expressed as an arithmetic circuit. How do we map this function optimally to our existing hardware fabric? Right, that's an open question. There's no definitive answer to that because a lot of this will be application dependent. So I think in the future what you can see are accelerators that arise for different domains, whether it's search or whether it's machine learning. Just as we've seen domain-specific accelerators in things like machine learning and encryption. One of the good things here is that there's no branching in the encrypted domain. So, for example, there's no way for me to do a comparison of two values and then branch in the encrypted domain. Because if I were to do a comparison and branch, that would reveal something about the data. So there is no way to branch all of your logic. If you have any branch full logic, that has to be converted to a branch-free. The branch-free logic. The good news about, that's bad news because it's not always trivial to convert branchful into branchless. But the good news is that we don't need any specialized circuitry in the actual hardware to dynamically schedule stuff, because the whole graph and the whole flow of data should be known in compile time. So that puts a lot of emphasis on having good compilers that understand the hardware, are able to schedule that application graph in an optimal way on the target. And so this is sort of another view of what this looks like. This is a specific functional unit, and this shows.
Excuse me. So I have a question here.
Yeah. Go ahead.
Yeah. So does it mean like you can model let's say neural networks using these kind of computation, but not any other kind of machine learning things like this using trees or other things?
Well,
they will require some kind of branching operations, so.
Yeah. So in general, I think it is an NP-hard problem to take a branchful program and convert it to branchless. So I'm not specifically sure about decision trees, but if you think of lookup tables, lookup tables, in the traditional sense is branching, and it is possible to convert those to branchless lookup tables. But decision trees in particular, I haven't looked at. But yeah, certainly there's a known subset of problems that have been implemented that are branchful and have been converted to branchless and have been implemented as homomorphic functions.
And can you just say again, like what was the benefit of having a, so the previous slide you mentioned something about the good news. Can you just
well, the good news is that we don't need to dynamically reschedule. We don't need dynamic scheduling. Everything can be statically scheduled because we know exactly what the flow is going to be like at compile time. But the bad news is that all the logic has to be branchless. Yeah. It's good and bad. Okay, so this is just an example of one of the units that implements this operation called the residue base transform. And once again, it's just taking the math and trying to express it most optimally and encapsulate that in your functional unit. And then it's the problem of what is the optimal way to pipeline these units. So this, for example, is a simple multiplication operation, but there's a bunch of upstream and downstream ciphertext maintenance operations that need to be done prior to multiplying two polynomials and then after multiplying two polynomials. So what is the actual way to optimally arrange those functional units in a pipeline? And of course, different chips will take different approaches. This is just one example from a chip that was designed at MIT called Crater Lake. And then there's a pretty wide ecosystem of software libraries, starting out with probably HE. HELIB was this library here was one of the first libraries to come out, and then we saw a number of other libraries. Seal and OpenFHE, which is a repackaging of Palisade, seem to be the most popular libraries nowadays. And then we have some more libraries that are focused on, for example, accelerating homomorphic encryption on things like GPUs and things of that nature. GPUs are not always an ideal candidate for accelerating homomorphic encryption simply because we're doing real number arithmetic on a GPU, whereas we need to do finite field arithmetic, as you saw with these homomorphic encryption schemes. But nonetheless, people are sort of jerry-rigging real number multipliers to do modular arithmetic. But it's not always the ideal approach. Then there's other libraries that are focused on actually taking homomorphic encryption programs and targeting TPUs as well, TPUs and GPUs. This was done on, I think, Google Gen 6 or Gen 5 TPU. Yeah, so there's a pretty robust software ecosystem that's emerged, but like I said, there's no real chips that have taped out thus far, but we expect a few of them to be taped out this year. And then this is just to give you the view of what an actual software implementation would look like, and I think this is taken from SEAL. So underneath it, you need a big integer library, which is typically GMP, and then the number theory library. So if you want to do things like modular reduction, primarily Barrett reduction and things of that nature. Common library here that's used across a number of different FHE libraries is NTL. And then on top of that is the homomorphic encryption library, in this case SEAL, and then the actual application, for example, the CNN, the MLNetSec2025 that we saw earlier on. Okay, so I don't know if we want to get into this. This is getting into a specific application for doing encrypted transformers. In other words, encrypting the weights of the transformer and then doing inference on encrypted weights, but I'm not sure if we have time for this.
I think we're running late.
We're running late? Okay, so I'll just stop over here and you can take it up later on in the workshop if there's any additional questions.
Maybe practically useful, we have to do some kind of compiler optimizations. Then compiler optimizations or circuit optimizations or something.
Right.
So can you give some insights like hardware works already in that domain?
Yeah, I think people are doing different types of circuit optimizations, like unrolling loops and things of that nature, and then really what it comes down to, for example, if you're doing matrix multiplication, you might naively think that, well, I just multiply a row by a column, and then I get the element. That's not necessarily the most optimal way to express that circuit, and so there's a number of different ways to slice across the matrices, across the tensors and the multiple. But yeah, I would imagine there are similar optimizations depending on the application.
Yeah, so that's what I was alluding to. So depending on the domains, you might have very counterintuitive ways of optimizing things sometimes.
Different ways of optimizing things, because ultimately, whatever you're doing is polynomial multiplication and addition, and those polynomials are just vectors, whereas tensors are not vectors; they're multidimensional objects. So how do you actually factor a tensor into a linear polynomial? Well, there's different ways to do that, and that'll have different performance implications in the encrypted domain.
Okay. Thank you.
To say ECC kernel operations, maybe.
Yeah, other than the sizes of the polynomials, what you saw is like just addition and multiplication of polynomials, right? So we're not talking like, we talk about ECC, or if we talk about RSA, we're talking about modular exponents. And modular exponents with 8K RSA modulus, well, that's pretty heavy, right? Whereas over here, we just like, if you looked at the encryption, I take the secret mask and I just add the message polynomial. So I'm just adding coefficient-wise addition of polynomial, right? So that's much lower overhead than like message to the power 65537 modulo 8K bit RSA modulus. Yeah. But then what happens is the expansion in the data, that's where you take the hit. When it comes to doing homomorphic operations themselves, like multiplication.
And one more question is in this homomorphic encryption. So how is the forward secrecy or non-plain text attacks? Like how is it good against them?
Well, if you talk about CPA security, so CPA security is preserved because you're going to add a new random error term to every encryption. So that means if you encrypt the same message twice, the ciphertext will look different. And that's a requirement for semantic security of CPAs, chosen plain text attack security. These schemes are not CCA secure because by definition you're modifying the ciphertext, whereas CCA secure schemes have to be able to detect any modification and disallow any modification of the ciphertext. But yeah, these schemes are CPA secure. They are secure against chosen plain text attacks.
Okay. What about like if the key is compromised, the earlier key is compromised and
You mean forward secrecy?
yeah.
Yeah, well, I mean, the only way to do forward secrecy is just to keep rotating your keys, right? And that would apply over here as well.
So the secret mask is the one which
The secret key, the secret mask is A times the secret key. A is a public parameter. Yeah, so you have to re-rotate your the secret key for forward secrecy.
is
Sir, I request Dr. Subramaniam from CSE department to hand over the goodies to the speaker.
Sir, come to middle, sir. Just wait, sir. Just wait.